All right, I think you can start slowly to tell us what you're going to present today.
Yeah. So the idea is to have a small workshop about Kubernetes. It's just it's targeted for people who know already a bit, on containers. But if you are not familiar at all with Docker, you should still probably get it. I do have the first part where I talk a bit about the containers and why we needed containers in IT. You should still be able to follow. I hope so. And then the goal is really to present Kubernetes and how it works, what it's doing, and why is it so in trend, I would say. So should I start or?
Yes, please, Arthur, feel free to start. And let's try to start with a very high level, because like if you can do like a 5 minutes very high level to present what is the space. You need to remember you have people like me, like Matt in the call. So I think, or like Jan. So like if you can go very high level for 5 minutes, and I think how it was, it would be great.
Gradually, yeah. We start with absolutely non-technical thing, and we'll finish with configuration and things like that. So
okay,
that's for everyone. Okay, so let's start an introduction to the world of containers and orchestration. So firstly, I just want to start to introduce what are containers and why we needed them in the first place. And secondly, I'm going to start talking about Kubernetes. And in third, I don't know if we had time, but I have a small demonstration ready if we still have time, or we could do a question instead of that if that's too short. So let's start with the introduction to the containers. So in the old days, the very old way to run softwares on the cloud or any production system was to run directly softwares on the server. So it has a lot of drawbacks. The first and the major one is that you have a strong environment drift between your local environments and your production environment. So that basically means that all your dependencies and things like that are not going to be the same, which could cause crashes that you cannot control, because it could work perfectly fine in your local dev computer, but ending up crashing completely on the production. And the other drawbacks is that it's very complicated to deploy, because you have to set up all the servers to install all the dependencies. And that makes the whole system very complicated to scale, to manage a different level of charge. So we kind of upgrade and we went to the virtual machine, which solves some issues. So the idea is to have your physical servers. On top of this server, you are running virtual machines, and inside this virtual machine, you have your own software. So we are adding a new layer between that. This solves some issues because the environment drift is way smaller, because you can install and control everything inside your virtual machine image. So you set up your virtual machine with every dependency you need. You snapshot this virtual machine, you create an image based on it, and this will be fixed, and this will always work, because it worked one time, it will work always. And this still has some drawbacks, mostly on deployment cost, because it's very complicated to start and create your virtual machine. So you need a lot of things to create the virtual machine in the first place. And then at each time you want to start to scale up, it will take a lot of time, because you'll have to completely virtualize a new computer. So that takes time. So we needed a third solution, which are the containers. And this solution needs to be with a small environment drift, so reuse the same advantage of the virtual machine, but it also needs to have a small deployment cost, so that needs to be way faster than virtual machine. And in fact, the name containers is not chosen randomly. It's based on the same idea of the real containers in the real world. So in the real world, a containers is a standardized object that you can use for storage and transportation. So inside this big giant box, you can put whatever you want. So that could be pallets, barrels, or any other thing you would like. These containers, since it's standardized, you can use it on any transportation system you would want. So that could be a truck, a train, or a boat. And in our idea for the IT world, the containers is just this metaphor. So in this example, the code and the dependency will be the thing you store inside your container. So that would be your pallets and your barrels. The container by itself will be the container engine you want to use. So we will see that there are more than one, but there's mostly one that is very famous, which is Docker. And your transportation system is your environment on which you're gonna run your code. So that could be your local dev computer, a virtual machine, a cloud service, or just basically a server. So with all I said, that could make you think that the containers are kind of the same as virtual machine. It's not the case, mostly because they are not running on the same layer. So if we take a look at the schema, on the virtual machine layer, on the virtual machine side, we can see that we have a layer additional. So the virtual machine, the way that works is that you have your physical infrastructure. So that could be a server, an EC2 you are renting on AWS. On top of that, you're gonna have your hypervisor. So it's kind of an operating system, but its only goal is to manage the virtual machines. And on each virtual machine, you're gonna have your guest OS. So that could be a Linux, Windows, or even Mac OS. This is a completely entirely managed operating system. So there's everything that is re-emulated. So you have a kernel and everything running inside. And inside your virtual machine, you're gonna find your binaries and libraries. And then finally, you're gonna have your application running on top of that. For the container side, the layer we are removing is the guest OS. So the containers are almost the same. We are still running on a physical infrastructure, so we're gonna still need to have a server running everything. On top of that, you're gonna have your operating system. So that will most likely be a Linux system, but could be Windows too. And inside this operating system, you're gonna have your container engine. So it's really a software that is running on top of your operating system. So you could install it on your laptop right away. And the container engine will gonna just simulate and gonna handle the CPU isolation to manage multiple processes. So it's gonna have all the processes. So that could be your applications and everything you want to run on Docker. And yeah, so the most famous container system at the moment is named Docker. It has been created in 2010, and it's really have been launched or released. The first version was released in 2011, so it takes basically 1 year to develop and make it available. For the fun fact, it has been created by 2 old students from our school, Epitech. So it's Solomon Ikes and Sebastian Pal. And they had a lot of experience in this domain because they created the first platform as a service system in France. And they had a lot of issues with the technologies they had at the time. So it's a bit like the first slide I've shown. So they created Docker to solve their own issue in the first place. And they see that it has a lot of interest. And so they decided to develop more Docker than their own platform. And yeah, so Docker is basically just a CPU isolation management system. So it's something that created in the end of the 90s by Linux Foundation. And the main idea is just to have another layer on top of your operating system that's going to isolate all your processes inside your computer. And so that the main advantages is that it can make your processes not seeing each other. So that's like they would run in a virtual machine, but they are isolated, so they can see each other, and that's the main advantage is for safety reason, because you don't want to have your software talking and seeing other software they should not do. And Docker is also the first one to implement an image system. So with the Docker file system, the idea is to streamline the image creation process. So for a virtual machine, creating a new virtual machine is very complicated because you have to run your virtual machine and you have to set up everything and then snapshot it. With Docker, it's way easier because you can define everything as a file. So you define all the steps you want to create. So that's basically just running scripts. And you can create the image with this file, and it will be static. So since at the moment of the file is working, the file will always work because everything is running inside containers, and the containers are static in time. So yeah, so Docker is really the most famous one. It's the one that creates a force and architecture. And the reason Docker wanted to make containers droppable, so they decided that the best way to manage architecture, complex architecture, is to make one services running per container. So in this example, you have a very basic application where you have a node application. This application is fronted by an Nginx service. The node application can also talk to a Postgres database, a Redis database, or some other services are included that are Prometheus and Logstash. So those are services for metrics and most DevOps activity. And the reason of having one service per container is that we can just drop the containers if they are running badly. So if our node application, for example, is starting to crash, we can just drop the containers and request a new one, because it's very easy and it does not take a lot of resources to request and ask for new containers. And Docker has been the first one to introduce the system of networking within containers. And the idea behind that is that since you can have multiple applications running inside isolated containers, you still want them to communicate between them. So in our example, we would like to have our node application talk to our database. And so Docker introduced this concept of networks. And with the networking, it's creating a new layer of IPs. That's a bit technical, but the idea is to have another layer of networking inside your own computer. So you have your local home network, and inside your computer, you have another network that is managing all the different containers. So the node application can talk to the Postgres one or the Redis one without any issues. And this architecture is really great because you can have any pod replaced as demand without impacting the complete architecture. So if the Redis is crashing, for example, we can just request a new one without having to have the node application not available, or the Prometheus one, or anything. But the drawbacks is that it became more and more complex to manage complex architecture, because if you have every application running as independent pod, as independent container, you're gonna have some issues if you have a very complex architecture, because you're gonna start to have a lot of application and different containers running everywhere. So we started to need a solution to manage complex architecture. So there has been a few one before Kubernetes. There has been Docker Compose and Docker Swarm which are both products of Docker by them. But they are very limited in comparison with what Kubernetes can do. So that's really the reason why Kubernetes today is really the most famous one. But Docker Compose and well, Docker Swarm is not really used in production, but Docker Compose can be great to deploy small architecture. So if you have small issues you want to, small deployment stack you want to do, Docker Compose is still a great option. But Kubernetes will most likely be your choice if you have complex applications to deploy on the cloud. So yeah, what is orchestration and what it has to do with Kubernetes? So Kubernetes is a project that started initially in 2013 and has been released in 2014. It has been created by Google, and it's not managed anymore today by Google. It's managed by an independent organization that is named the Cloud Native Computing Foundation. Yeah, that's it. And so it's a foundation which is the daughter of the Linux Foundation, so it's still very open source minded. The goal of Kubernetes is to manage Docker containers. So the real goal is to provide a system of static configuration that can manage an entire architecture of containers, networking, and configuration. It has been designed in first place to work with Docker, but since 2016, the core system of Docker, of Kubernetes changed, and it can now work with any compatible container service. And in fact, at the moment, when you install Kubernetes, it's not even running by default with Docker. So they are really separated projects, but using the same technology at the base. And one thing very important, in particular with Kubernetes, is that it's loosely coupled. So that's how the documentation defines it. But what that means is that any internal component inside of Kubernetes is designed to use interfaces. So everything is abstracted. In the fact that means that every internal component can be replaced with other components, or you can even develop your own components if you have specific needs that you cannot solve with the default ones. We'll see some example of that just after. And before we dig inside the magic of Kubernetes, it's very important to know what Kubernetes can do and what it cannot do, because it's not a magical tool that can do everything inside your organization. So the first thing that Kubernetes really excels at is the service discovery and load balancing. It's really where Kubernetes shine. So it will provide you with its own DNS server. This DNS service will be used for internal networking communication. So we'll see just after, but when you have multiple pods and multiple containers that need to talk to each other, the way you're gonna do it is using DNS. Each pod is gonna be named inside your cluster, and the issue you could have is that since you have your container, they are all gonna get different random IPs. So you're gonna need a strong mechanism to make them talk to each other, because you cannot just use IPs since they're gonna be changed every time you redeploy your configurations. So you can, the way Kubernetes solves this issue is with DNS. So every pod, every container is gonna have its own DNS name, and you can use this DNS name to talk between each services. You also have a strong tagging mechanism that is used mostly for service discovery. It's gonna work exactly like AWS do it. So every resources inside your Kubernetes cluster and configuration can be tagged. And with those tags, you can do some magical configuration to automate setup. That's for example, if I could give one, it's for Prometheus. So Prometheus is a system that collects metrics inside your containers. It's an optional service you can add. To configure all your containers for the metrics collection, you can just add new tags, and the metrics service is gonna see those tags and is gonna know, because they are defined in the documentation. The metrics collector will get your metrics based on the tags you provided to it. And I could also provide you with load balancing. So if you have application that scales, you're gonna most probably want to have a load balancing between those services. If you have like your node application in my previous example that you scale up to 3 different replicas, what you would like to do is to have your user use at the same rate the 3 different pods. So that's something that Kubernetes would do for you. Kubernetes is also very strong with storage orchestration, so it can manage for you all the volume declaration. So each time you create new containers, you can define in the configuration that those containers need a volume of 10 gigabytes, for example, and Kubernetes is gonna automate for you the volumes creation. I can also work with different storage providers, so you can store your files on local storage directly on your servers, on your nodes. You can also use network storage or cloud storage. All of that are interfaces, once again, so you can really install or even deploy, create your own storage system. Kubernetes is also very strong with automated rollouts and rollbacks. So when you are updating your application, Kubernetes is gonna provide you a system that can deploy gradually your updates. So firstly, you're gonna deploy on a new sets of containers you're gonna say that 15% of the traffic are gonna be translated on the new updates. And if everything is correct, you can upgrade to 30%, 60, and then 100%, and you remove the previous version of your cloud deployment. It can also provide safeguard and automatic rollback. So if you are detecting that anything go wrong when you are deploying your updates, you can just go back to the previous version, work on your side to fix the issue, and then deploy this new version again. Kubernetes is also very strong with what's called bin packing. So it's a concept in IT to make resources used smartly. So the basic idea is that you will be given a limited number of resources on your nodes. So you're gonna have a limit of CPU, RAM, or storage you can use, because we are running still on physical architecture, physical servers. So Kube can provide you a mechanism to optimize the utilization of those resources. So either by spreading them. So if you have like 2 nodes that have 2 CPUs and 8 GB of RAM, you can make Kubernetes spread the resources on all the nodes to use, to avoid that one node is completely filled with resources and the other is unused at all. Or you can also make the deployment be regrouped. If Kubernetes thinks that we can remove one node of your entire cluster to avoid useless costs, Kubernetes can detect that and it can say, okay, so I can see that I can regroup all those resources on those 3 nodes and remove the 4th one, so we can pay less because we have a server running in less. So you can also have self-healing. I mean, Kubernetes is also very strong with self-healing. So Kubernetes will always manage your container and will do an automatic health check mechanism. So you can define 2 different health checks. In fact, you have a liveness probe, So the liveness will indicate to Kubernetes that your containers is working fine or not. If the liveness probe fail, Kubernetes will immediately kill and start a new containers, because it's basically sending a signal to Kubernetes that this container is broken and will not work anymore. And you also have a readiness probe. So this, if you are failing the readiness probe, the only thing that's going to happen is that Kubernetes is going to stop sending traffic to this container in particular. So it's very useful when you are scaling up or down application. You don't want to send traffic to an application that is not yet ready to receive traffic. So that's where you would say that your liveness probe is okay, because your containers is in fact working, is starting up, but it's not ready to receive traffic. So we'll say that the readiness probe is crashing, but that's okay because Kubernetes can see that and will just wait for your container to be ready before sending traffic. And the last one is for secret and configuration management. So that's another point where Kubernetes is very strong. You can store any configuration or any secrets you like directly inside Kubernetes. You are not forced to do it. You can also use external services. So for secrets, I can think of Secrets Manager of AWS, but that's something that is directly integrated within Kubernetes. So that's still something great to use. There are still things that Kubernetes won't do for you, and it's by design. So it's not something limited. It's really that the foundation behind Kubernetes doesn't want Kubernetes to do that. So the first one is for CI/CD, so continuous integration and continuous deployment. Kubernetes will not manage that for you, but to be clear, it's only the deployment workflow that it won't do. You can still, for example, GitLab or GitHub Actions can still be deployed on Kubernetes, but the only thing that's going to be deployed, it's the runner. So it's the small software piece that's going to handle all the steps you wanted to do. But the deployment is still managed by GitHub Actions or GitLab or CircleCI, any software you'd like to use. But the thing to remember is that Kubernetes is not the software that's going to manage everything for you. It's just going to run the software that could manage that for you. Kind of the same as the last point. It's basically anything that is application level are not going to be managed by Kubernetes. So that means that it's not going to provide you with a message queue system, a cache system, or database system, or anything that are application. You could still run a database, a message queue system if you would like to, but you'll have to create your own deployment on thing for that. That's not something managed initially by Kubernetes, but that's something you can add with your own configuration. So if you want a message queue, you can deploy a MQTT system. If you want a database, you can deploy a MySQL. That's really up to you. Kubernetes also does not provide any logging solution. The only logs you're gonna have are what are called the hot logs. It's the direct output of your running containers. So as soon as your containers are shutting down, you're gonna lose those logs, but you can still see them running in real time if you need to, if you have to do hot debugging. But if you really want to have complete logging with a strong go back in time mechanism, you should use external software such as CloudWatch, not for naming it, but as AWS services, you have CloudWatch logged, which will do nicely. And the last point is for anything related to the host of your nodes. So Kubernetes won't provide any mechanism to update or manage your host nodes at all. That's still up to you. If you want to manage your own Kubernetes nodes, you will still have to update your Linux. You will still have to manage everything network related. So it's not gonna manage your firewall for you. Those are all the things you'll have to do on your own, on your Linux machine. As I said in introduction, Kubernetes is very split in a lot of different components, and really basically any layer of management are split in different components, which there are not all the components in this diagram, but there are at least a lot for starting. And what is to be interesting about this diagram is that, as you can see, the components required for having a worker are the same as the one required for having a manager node. So you can very easily make a worker node become a manager node and the reverse. So we have two kinds of components. We have the control plane components, which are the components that are needed for having a worker node. And we have the running the worker plane components, which are the components required for having a worker. So the first component is the Kube API server. The Kube API server is, have its name perfectly named. It's just an HTTP API that will allow you to manage the cluster. That's your entry point to send up new configuration and update the current one. You have etcd, which is a simple key value storage system. It's used internally by Kubernetes, so to save and manage all the configuration within the cluster. So you cannot access it directly, or you should not access it directly, but it's going to be used by all the internal components to update and manage the cluster. You have the Kube scheduler, which is a simple component that decide where to deploy the new workloads you ask. So it's based on policy and also on the resources you have available. And it's a very simple component that is requested by the internal components to, let's say, start a new Nginx somewhere. And the Kube scheduler is the one that's going to say, okay, I have this node that is ready to receive a new charge, a new workload. So it's where it should be deployed firstly. And the final one is the Kube controller manager, which is a component that automates any action inside the cluster. So if, for example, you have workloads or containers that became unavailable, it's the one component that's gonna update the load balancing pool, so to stop traffic to it, to stop sending traffic to it. And it's also this component that's gonna order a replacement of the damaged container. And in the same ID, you also have the cloud controller manager, which is doing the same actions, but with the cloud in mind. So it could be the components, for example, that could create an EBS, so an AWS Elastic Block Storage volume, when you are requesting a new volume inside your cluster. So it's basically very cloud related. So if you are deploying an EKS, which is the Elastic Kubernetes service, which is the Kubernetes system or service provided by AWS, the Cloud Controller Manager is going to be a tool that is developed and managed by AWS themselves. If you're going to go with GCP, it's the component deployed by GCP and things like that. On the node components, we have the kubelet. So all those components are just required for having a worker node. They are not necessarily, I mean, the previous one are not necessarily required if you are just running a worker that's gonna manage your workloads. So the kubelet is a component that interacts directly with the container service. It's the one component, kind of Docker, that's gonna manage, start, stop, or remove the containers. And it's just doing this simple task. And so you have the kube proxy, which is the components that manage the networking inside your nodes and your cluster. It can apply network rules to allow traffic between all the pods. And the kubelet components is the components that gonna talk to the container runtime. So the kubelet is just the abstraction of talking to a container, and the container runtime is the actual software that is running the containers. So the container runtime could be Docker, it could be containerd, or there's also another one famous, which is CRIO, but those are really the three main ones that are used in the cloud today. But yeah, what's to remember is that kubelet is just the abstraction. So kubelet can say, okay, start, or okay, stop now. And it transmits that order to the container runtime through an interface that is named the container runtime interface, the CRI. And that's how you can have multiple container runtime engines working within the same kubelet, because there are this single interface between them. So to interact and to manage your cluster, you have multiple ways. The first one is using a CLI tool, which is named kubectl. It's the official product deployed by or distributed by Kubernetes themselves. If you go to the documentation, all the examples are gonna use the kubectl CLI tool. So it's really the one you would like to go with. But you have other solution. The second one is the named dashboard UI. It's an official GUI for Kubernetes that is deployed, managed by Kubernetes themselves. They are the ones who are managing the code. And it's just a simple web interface where you can see all things that are deployed and running inside your cluster. And you can also deploy new resources with files. And you have third-party solution. So the one I'm using personally is Lens, which is really great. But it's GUI, a software you run on your own laptops, and it's gonna provide you with an interface where you can see every resources, kind of dashboard UI, but dashboard UI is running inside Kubernetes. Lens is running outside, so a Lens Kubebox or Kubernetes are all running outside of the cluster and are just communicating with the Kube API server for you. So on the orchestration side, Kubernetes define all its configuration as objects. So you are defining and you are creating those objects with files, and Kubernetes consider that as record of intent. That's how it's defined in the documentation. So you are basically asking Kubernetes to do things, and Kubernetes will do anything it can do to make that thing happen. But sometimes it cannot be, because you could be asking for impossible thing, and that's not something Kubernetes will really warn you for. So if you are asking something that it's not possible to do, Kubernetes will not say anything. It will just try it to do, and it will try it in loop just until it works. So that's really something you should check when you are working with Kubernetes, is that sometimes you could make something that is not possible, and Kubernetes will not warn you that. The configuration can be imperative or declarative. So that's really the two ways you can interact with the cluster. The first one, the imperative one, is just a command you can start, you can type. So you could just say in commands what you would like to create. The issue with that is that you are just gonna create these resources. And so since it's command line, it's not really great for managing it inside the Git repository. So if you have to have something that you can replicate. So for example, you are working for a project for a client, and you're gonna want to have something that you can redeploy if necessary, or it's gonna be something that's gonna have to give to the client. So I would not recommend going with the commands. And for that, Kubernetes also fix that issue, because we can define all the different objects you want to create as files. So files are great because you can store them in a Git repository. And you have two ways of creating those files. So either using imperative declaration. So you are just declaring that you want to create these resources, but that's not really great because you cannot update them as soon as they are created. They are static inside your cluster and you will not be able to update them. And you have the declarative method, which will allow you to create a new object and then you can update it. So if you update the declaration file, Kubernetes, when you will apply the updates, Kubernetes will merge the new version you give it to it, and it will check with the version running in production at the moment, and it will merge the two files between them, and it will update the application like that. And thing to remember is that every object, every configuration you are declaring inside Kubernetes are plugins. So there are most of those configurations are declared as custom APIs. So that's plugins that you're adding externally that are not present by default within Kubernetes. And the fact that everything is plugins, that means that you can replace, you can plug or unplug them as will, and you can also replace them with other components if you are not satisfied with the default ones you are provided with. And just to have an example, so I won't go too deep in that configuration, but just to have an example to see what I'm talking about when I'm saying that it's object. So this is the configuration for deploying a simple Nginx container. So every configuration starts with at least two keys. So obviously, I didn't say it, but it is the YAML file. So every configuration are done using YAML. You can also do it with JSON, but official documentation always use YAML form. And if you go to Stack Overflow, you also always see YAML too. So I wouldn't recommend going with JSON. Just stick with YAML. It's great YAML. And the first key you always see is the API version. So the API version will declare from which API service you want to use and which version of this service you would like to. So in this example, we are going to use the service name apps, and we are going to use it with the version 1. The second key is the kind. So it's the type of the objects we want to create. So in my case, it's a deployment. And then you have the, not necessary, you will not find those keys every time, but you have the metadata, which are just data that you can stick to the object. So most likely you will find a name key. You also find a namespace because you can isolate resources using namespace. And in my example, I also have a spec key because that's how deployment works, but the spec key will most likely change based on the kind of object you want to deploy. And that's the internal configuration of the object. So in my case, I just want to create a new container that is named Nginx, and that will run the version 1.14.2 of Nginx. And I'm opening the port 80 to allow traffic going in and out. So there are a few APIs. I'm not gonna talk about all of them, but I'm just gonna talk about the workload APIs and the configuration APIs because that's most likely the one you're gonna use or work with. So the different objects you can create with those APIs are those ones. So the first one, the most simple one, is named the pod, and the pod is basically representing a container inside your cluster. So that's a bit of taxonomy, but it's really just renaming things that you already know. So just remember that the pod is a container. On top of that, you can have a replica set. So a replica set is an object that can manage a set of pods. So it's very useful when you have stateless application that you want to rescale. So you're gonna define your replica sets, and your replica set gonna create the pod for you. So the configuration you would pass to the pod, you can just give it to the replica set, and you can say, okay, I want 5 versions of this service, and the replica set gonna create 5 pods. The deployment is most probably the one you're gonna see the most. The deployment is going to manage the replica set for you. You are at least I've never seen that before, but you are very less likely to create a replica set. You always create a deployment, and the deployment gonna create the replica sets, and the replica set's gonna create the pod for you. So that's kind of a chain, but that's how it works generally. You also have the daemon sets, which is very useful for creating replica based on node basis. So if you have a service that you want to run one time per node that you are adding to your cluster, that's a daemon set you're gonna use. And the last one is the stateful sets, which is very useful for managing a set of pods. Kind of the replica set, but it's really designed for stateful application. So if you have a database, you are most likely gonna make it run with a stateful set, because it's ordered. So if you are ordering a rolling of the stateful, it's gonna firstly destroy the old pod and then create the new one. So you won't have two different stateful sets running at the same time. The second API I want to present is the configuration, because you're gonna work a lot with that. So we have the configuration map and the secrets. So those are basically key values storage system. They are working very similar, but secrets are base64 encoded, but that's really the only difference you will have between them. And the fact that they are so similar is because for configuration simplification, and also for permission, because when you also have an ACL system inside Kubernetes. So if you have different objects, config map and secrets, you can just give access to config maps and not secrets, or the reverse. So that's really useful. Resource quota are just resource quota, but for namespaces. So you can say that different specific namespace can only use half of your CPU on each node. The HPA, or the horizontal pod autoscaler, is a system for managing the replication. You will give it a stateful set or replica set, and it's gonna manage automatically the scale up or down based on the metrics you are giving it to it. And the last one is the pod disruption budget. So it's just a simple system that's gonna manage the level of fault tolerance you want per pod. So you can say that this pod cannot have, or most likely, this stateful set cannot have more than 5 pods unavailable at the same time. That's very useful for managing rolling updates. And I'm not gonna go too deep inside networking within Kubernetes, because that could be the subject of directly its own specific presentation, because it's really complex. But on Kubernetes, networking is also abstracted. So you also have an interface for that, which is named the CNI, the Container Networking Interface. That also means that you can install different software, the different network software system. So you have Calico, Weave, or Flannels that are the most famous, but you have hundreds more if you are searching for it. And the only thing I'm gonna say about networking within Kubernetes is the 3 rules that are defined by the documentation. So if you want to deploy or create your own container network service, you'll have to stick to the 3 rules. So they are very simple. They state that every pod, so every container inside your cluster, must have its own IP. Any pod can communicate to any other pod on any other nodes, and any agents, so any internal components, can communicate with any pods on any node. So that's basically just saying that anything running inside your Kubernetes can talk to any other running components. And all that say is that if you are taking a look very briefly to the schema, if you have multiple nodes and multiple pods running on those nodes, that means that your CNI, so your networking interface, we'll have to provide you with a VPN system to allow communication between your different nodes that could be hosted on different region or even different continents if you are talking in cloud. So that's really up to you to choose your networking tool, networking software you want to use, but they are all gonna provide you with those same rules. So networking on Kubernetes is very simple because as soon as you have deployed your CNI, you have configured it correctly, you are not going to be worried about having a question like, can my pod join this one? Because yes, it can, because that's the rule dictated by Kubernetes. Just very brief points on how to communicate within the cluster. So if I retake my example of my node application that needs to talk to its database, the issue we have is that the node application cannot talk directly to the database because those resources are most likely be deployed with the deployments and a replica set. So the pod name is going to be random because that's how the replica sets works. When it creates new resources, new pods, it's associated with a random ID at the end. So we could set in the configuration of our node application to when it wants to connect to the Postgres database to use the pod name. So since it's random, we can give it as configuration. The major drawbacks, I think you see it, is that at each time we're gonna redeploy the Postgres database, we're gonna need to redeploy the node application too, because the name of the pod will change. So that's not ideal. The solution behind that, so we would like to use DNS between those two services, and the solution behind that is to declare a service for each pod, and this service is gonna have a static name. So in our database, the service could be named database, and for the node app, the service name could be just app. And on the node application side in the configuration, we are just giving it the DNS name of the service, which is static, and the service is the one that's gonna manage the load balancing for you. So it's configured to target the pods that could have a name with a certain prefix that you are sure is gonna be used by the PostgreSQL deployments. And on your node application, you are just going to target the service for connecting, or let's say that you're in the Postgres configuration, you're going to say the host name of the database is the name of the service, and the service is going to transmit the message to the correct pods, and it's going to handle all the rolling mechanism if you are updating the database and the pod is going to be replaced. The service is going to provide you with a mechanism that will redirect the message to the correct pod. So yeah, as I guessed, I won't have any time for the deployment or demonstration. If you really want it, the repository is available on GitHub. I can send you the link if you want. But I think the repository is just named kubedemo. So if you look at the
maybe
GitHub
send
track,
it to the channel.
Yeah. I guess I should have it there. So yeah, so if you have any question, yeah, I do have a slide for that.
When it comes to alternatives, everyone always says, you know, the reason they go with alternatives is because Kubernetes is overkill. What's the problem with overkill?
Yeah, that came to my points. I can't remember. I think it was there. So most likely, if you have a small stack of application you want to deploy, you are most likely wanting to go with Docker Compose because that's really simple. If you have just like few things to deploy and not really caring about scaling up, scaling down, certainly Docker Compose is going to be a solution for you. But yeah, I would say that the problem with overkill is mostly you. It's do you really want to spend 1 or 2 hours more to configuring your architecture, or do you want just to create a simple YAML file and deploy it as on the go?
Yeah, that's kind of what I thought. Yeah. Another one when it comes to alternatives.
Yeah.
So like when it comes to alternatives, there's like different kinds of alternatives, right? There's like less complex alternatives like Swarm and Compose. And then there's alternatives that build on top of K8s to like abstract things away. So like Rancher, OpenShift. And then there's like straight alternatives. So like what, like I think like GKE, Mesos, and a few other, I can't think of them off the top of my head. It's still really early. I haven't looked into those like straight alternatives in a while, but are any of those looking promising in the terms of like challenging Kubernetes for its crown?
Well, Rancher is still Kubernetes, so it's using
it's just
different
built on top
components,
of
but
Kubernetes.
yeah, that's still the same API, so you'll still use kubectl to manage it, and object's gonna be the same. But no, as far as I know, there's no really competitors to Kubernetes for now, and that's most likely because everything is so modular and so replaceable that there's no need for replacement, because if there's something that you don't like inside Kubernetes, you can just rewrite it or use your own components. And that's, I guess, why there's no one. Yeah.
And I guess the first competitor, it's Kubernetes itself, because you have multiple versions of managed Kubernetes. We talk about Rancher, of course, as a AWS expert. By default, we go to EKS. And I think like this market, like going like, because I remember there was an announcement where you can run EKS on different clouds, for example. So is it like maybe the main competition, and where we're going to see the innovation? Where what about like the Kubernetes version of Google versus the Kubernetes version of AWS versus the Kubernetes version of Azure, and some other vendor still using the Kubernetes stack but providing different features? Do you see anything going that way?
Well, there are still very different between GCP and EKS, for example, but in the core, it's still the same architecture. So you still define the configuration as the same object, and so that will still be this one. So all your configuration is still going to be the same between the different services you can find on the cloud, or even that you can deploy yourself. So that I don't think that's really competitors for that.
Okay. Because
but what about Docker Swarm? Is it a competitor or
CloudFormation?
No, Docker Swarm.
Docker Swarm?
Docker Swarm. Well, Docker Swarm is really
Little brother.
Yeah, not technically, because it's very different, but it will be more closer to what you can do with Docker Compose. Docker Swarm is gonna be like Docker Compose with node management. So you can deploy containers on different servers, but that's really very basic. That stops there. So you won't have deep networking system. You won't have deep configuration system. But
so maybe for a beginner, it's easier to try Docker Swarm than level up using Kubernetes.
I don't think so. Yes, it's so different, and so you need to remember the marketing side of the product also. And I feel Docker Swarm totally lost the game on the Docker orchestration. And today I don't know anyone running it in production.
Yeah, that was my point. I don't know of any projects using Docker Swarm. So
I think in terms of beginners, I think it's easier to understand containers and then understand difficulties of containers in a production system and why container orchestration becomes important after understanding why containers are important. Containers at scale, I mean.
I mean, that's still great to know why or how containers work, but it's definitely not required to learn Kubernetes.
Oh, no, it's definitely not. But I mean, just to understand why Kubernetes, like, container orchestration is important. It's good to know why it was made in the first place to, orchestrate it.
Yeah.
In terms of Kubernetes, still, again, back on Kubernetes topic, like what's the future for Kubernetes? Like, I have trouble seeing like what they need to do to make like Kubernetes 2.0, but like, what does that mean?
That's a good question for start. I don't really know, to be honest, but I'm guessing that there are there's nothing I can think of that could be deployed more for Kubernetes, because everything is so modular that it's just gonna be new modules being created or deleted from Kubernetes to match the future requirements. But I'm guessing where Kubernetes is gonna be lost in the far future is for Web3, because Kubernetes is really a Web 2 software. And so if you are starting to talk about decentralized internet, maybe Kubernetes will change in the future, and Kubernetes of the future will be something that can handle and work on the decentralized internet. But yeah, for now, it's definitely a Web 2 product. So
good point. I didn't think about it from that perspective. Thanks.
Well, thank you, everybody. Arthur, I'm afraid we're gonna have to finish here.
Yeah,
thank you very much, everybody, and I hope to see you in the next workshop. And have a good day.
Thanks.
Thank you.